Okay, so here we have proof that every finite subset of k to the n is an affine variety. So first, a subset is an affine variety if it is the vanishing set, sometimes called the vanishing locus, of finitely many polynomials. Okay, so I need to show that every finite subset is a vanishing locus of finitely many polynomials. So example, the point 2 on the line, 2 is the vanishing set of the polynomial x minus 2. Okay, here's another example. Let's say I'm at the point 2, 1. So the set with the element 2, 1 is obviously a finite subset, it's just one point in the set, and it's equal to the vanishing set of the polynomials x minus 2, y minus 1. So it's where both of these are required to be 0. That only occurs at the point 2, 1. You can think about this as the intersection of these two lines, the vertical and horizontal lines. Okay, but what if I want to take something more complicated, like let's say I'm on the line and I take the point 2 and the point -1. So the set 2 and -1, a subset of k to the 1, is the vanishing set of what? So if I take the polynomial x minus 2 times x plus 1, so I'm multiplying these polynomials, then you can check that in order for this to vanish, either x has to be equal to 2 or x has to be equal to -1. And so that's why this statement here is correct. So I can get 2 points by multiplying the polynomials that would have given me each individually. Let's take the point 4, 1 and the point 2, 2. What if I want to get both of those? Okay, so then what happens is that, okay, so what I need to do, okay. The point 2, 2 alone would be the vanishing set of x minus 2, y minus 2, namely the vanishing set of two polynomials. Let's call them f1 and f2. And this would be the set that just contains that single point. Now the vanishing set of x minus 4, y minus 1, let's call this g1, and g2, would be the set of just one point, namely the point 4, 1. Okay, to get both points, we need to multiply. So we'll take the vanishing set of f1, g1, f1, g2, f2, g1, f2, g2. So, I mean, in more precise detail, v of x minus 2 times x minus 4, comma, so this is one polynomial, I multiplied some polynomials together. Now I need to list a second polynomial, and that will be f1g2. So this is x minus 2 y minus 1. Okay, that's the second polynomial. Then my third polynomial will be f2g1, x minus 4. And then finally f2g2, y minus 2, y minus 1. And so let's check this. Does this give what we want? Well, first, does the point 4, 1 go in there? Well, we have to check, do all of these vanish at the point 4, 1? So at 4, 1, all these vanish. We get 4 zeros. Why? Because the 4 goes there, and the 4 goes there, but then the 1 makes it vanish there and there. And so it works. 4, 1 is in this vanishing set of these 4 polynomials. And similarly, so is 2, 2. And importantly, the point right here, which is the point 2, 1, is not. So why is 2, 1? Well, this vanishes at 2, 1, because when I plug in x equals 2, I get 0. This vanishes at 2, 1. But look here, this does not vanish at 2, 1. This does not vanish at 2. Oh wait, yeah, it does. So really, it's just this polynomial here that that makes it so that we don't get 2, 1. And that's great because we didn't want 2, 1. We just wanted those 2 points. Okay, so I'm going to write in general, if the V is the vanishing set of F1 through Fn, and W is the vanishing set of G1 through GS, or GM, let's say, then the union is the vanishing set of all possible products Figa for all I and j. This is just a shorthand way of writing the vanishing of F1, G1, F1, G2, F1, GM, F2, G1, F2, G2, F2, GM, all the way down to Fn, G1, Fn, G2, all the way to Fn, GM. That's a lot to write, so instead we just write this. All pairwise products. Okay. So now let's go back to the original question. Prove that every finite subset of Kn is an affine variety. Well, so proof. Since any point P equals, let's say, P1 up to Pn in Kn is equal to V, the vanishing set of x1 minus P1 xn minus Pn, every point P in Kn is a variety. By the previous problem, we know unions of varieties are, well, we know the union W is a variety if V and W are. So, need to show that V1, V1 union V2 union Vk is a variety if each Vi is a variety. But this union from I equals 1 to k of the Vi's is equal to V1 union up to Vk minus 1 union the kth. So I'm just grouping the first ones. Then by induction, the result follows. Okay, so I'm leaving out a little bit of steps, but I mean, this is basically how induction works. We know the base case of V1 union V2 is base case, maybe. Or maybe you could even call, we could call this the k equals 2 base case, but then just V equals a point is base case of k equals 1. And so putting together finitely many points is the induction step. And assuming the result is true for k minus 1, we use star, where star is up here, this equation, to get the result for k. And that's finally the proof. So I showed that 1 point was a variety. We know that the union of two varieties is a variety. So by induction, any finite union of varieties is a variety. That's what we can show by induction. So did I answer the exercise? Prove that every finite subset of Kn is an affine variety? Yes. Yeah, in fact, I think I showed a little bit more that finite unions of varieties are varieties. Okay. That was my answer.